All right, so we're going to start section 5 of chapter 2. This is actually going to be the last section that we cover in chapter 2 before our test. So right now we're on pace for our next test to be 1 week from today. If I move the test, I'll push it back. I will not move it ahead. Like I said, this is our last section. So I want to go over this section today, probably get an activity on Wednesday, review on Friday, test on Monday of next week. All right, that's a tentative schedule. Like I said, if I move it, I'll push it back. I will not move it ahead. So right now, we're on pace for test 2 to be on October 11th. It's going to cover sections, chapter 2, sections 1, 2, 3, 4, and 5, or sections 1 through 5. All right, so we've been keeping up with the lectures for after 2.2. Remember, 2.1 and 2.2 is basically using that limit definition of the derivative. 2.3 is where we start our formulas, the sum formula, the difference formula, product, and quotient rules. 2.4 is the derivative of trigonometric functions. You can bring that chart with you, the derivatives of trigonometric functions. I do not expect you to memorize the derivatives of sine, cosine, tangent, cotangent, secant, and cosecant. So all the way up to this section, the chain rule, which is typically the one that gives us the most pause. The chain rule is for the composition of functions. So first, we want to formally define it. All right, so by definition, the chain rule, or how we find a derivative of a composition of functions, it states that if g is differentiable at x and f is differentiable at g of x, then the composite function f, which is f composed with g, defined by f of x is f of g of x, is differentiable at x, and f prime is given by the product. Or this is the formula: f prime of x, the derivative what we're looking for, is equal to f prime of g of x times g prime of x. So that's in the Newton notation. In the Lebanese notation, if y is equal to f of u and u is equal to g of x are both differentiable functions, then dy dx, or the derivative of y with respect to x, is equal to dy du times du dx. Those last few are choosing to copy that down, get it copied down. Remember, this is that formal definition of the chain rule. It's given to you both in the Newton notation and in the Lebanese notation. But there is a shorthand definition or another alternative definition that you can lean on that typically makes more sense in the beginning. So if you understand this formal definition, great. If not, then what I would suggest you do is to lean on this shorthand definition, and it'll get the answer that you're looking for using the chain rule. I want to make sure I'm not going too fast. Anybody still copying from up? So that shorthand definition of the chain rule, or the one that I would suggest you lean on in the beginning. Remember that the chain rule is how we find a derivative of the composite function, or a function inside of another function, namely f and g. So we have to start thinking about these functions in terms of inner and outer functions, or the function inside and then the function on the outside. So the chain rule, or the shorthand definition of the chain rule, will be the derivative of the outer function at the inner function, and this being multiplied or times the derivative of the inner function. So the way we need to look at these functions are in terms of inner and outer functions. And typically, it's just as simple as looking at what's inside the parentheses. If there isn't parentheses, we can use some algebra to introduce parentheses into the problem. Whatever's inside parentheses, the inner function. And if we treat the parentheses like a variable itself, or if we just simply look at the parentheses as x, then whatever's on the outside of parentheses, provided that we input that x for parentheses, is my outer function. That's a lot to say. There's not very much to do, but it does take a little bit of adjusting until you get to the habit of looking at terms of these functions as inner and outer functions. Because up to this point, we've basically been asking ourselves, what are we doing with these differentiable functions? Either added, subtracting, multiply, or divided, and we had a formula for it. Sum, difference, product, and quotient rules in terms of derivatives. All right. So the best way to do this is kind of get our hands wet. I'll start working with some of these problems. Is anybody still copying the shorthand definition? I would suggest that you had that shorthand definition near you when you first start working these problems. All right, so in example one, this is a good candidate. For example one, we're asked to find f prime of x if f of x is the square root of x squared plus 1. All right. Now the first thing that I would do, one, is recognize that this is a chain rule problem by remembering that the square root of x is the same thing as x to the 1/2 power. Said that to say that the square root of x squared plus 1 can be rewritten, still dealing with f of x. They're not working on a derivative yet. We can rewrite f of x as our radicand x squared plus 1 raised to the 1/2 power. This is when we've introduced our parentheses, and it makes it a lot easier for us to identify the inner and the outer functions. All right, so here, my inner function will be x squared plus 1, or what's inside my parentheses. My outer function, we're going to treat the parentheses like x, so everything inside the parentheses, including the parentheses itself, becomes a variable, specifically the variable x. So my outer function would just simply be x to the 1/2 power. All right, so once again, my inner function, what's inside my parentheses. My outer function, I treat the parentheses and what's inside of it, replace it with a variable, and take note of whatever's on the outside of the parentheses. So here, the only thing on the outside of parentheses is the power of 1/2. So I treat it like x, the parentheses I mean, and I raise x to the 1/2 power. Are there any questions on how I got the inner and the outer functions in this example? All right, so remember, this is pretty straightforward here. But remember, if you can't label the inner and the outer functions, we can't start the chain rule. If we can't start it, then how can we finish? All right, so we have our inner and outer functions. This is when I will lean on that shorthand definition. So remember, the shorthand definition starts with the derivative of the outer function. So my outer function is x to the 1/2 power. So we're starting on that derivative. Now we're working on f prime of x. Now the derivative of the outer function, or the derivative of x to the 1/2 power, we'll be using that general power rule, bringing our exponent out front, decreasing the exponent by 1. So here, that 1/2 goes out front. I'm going to leave an open parentheses for x, because remember, we introduced that x to encompass the parentheses. And this does get taken up in that shorthand definition. Raised to the 1/2 minus 1 power. And we know 1/2 minus 1 is negative 1/2. All right, so that's the first part of that shorthand definition. We've done the derivative of the outer function. When it goes on to say at the inner function, all that means is what was inside my parentheses goes inside my parentheses again. So this is the derivative of the outer function at the inner function, means what was inside x squared plus 1 goes inside the parentheses again. Picking up on that shorthand definition, we've done the derivative of the outer function at the inner function. Now we're going to multiply it or times the derivative of my inner function. So my inner function, x squared plus 1, the derivative of x squared will be 2x. The derivative of positive 1 will be 0. No need for us to write it. All right. So we've applied the chain rule appropriately here. Now we just need to look to simplify if possible. Any questions on how we got 1/2 times x squared plus 1 to the negative 1/2 power times 2x? Yes, ma'am. All right, so remember that shorthand definition, that last part, we've done the derivative of the outer function at the inner function. Then we're going to multiply it. This is where the 2x comes from, the derivative of the inner function. So my inner function, x squared plus 1, derivative of x squared, 2x. That's where that 2x comes from. Derivative of positive 1, 0, so there's no need for us to write it. All right, so that's where the 2x came from. Any other questions though? Because remember, I know this chain rule, it gives reservations in the beginning because it's a different way of looking at the problems, not necessarily that it's any more difficult than any other rule. So any questions up to this point so far? All right. So now we just need to simplify this product. 1/2 times x squared plus 1. Obviously that negative 1/2 power, we don't want negative exponents. We can use some algebra to get rid of that. And we also want to multiply any factors that we can. All right. So first, we have two factors that we can multiply, 1/2 and 2x. If it were me, I'm going to go ahead and handle that x squared plus 1 to the negative 1/2 power. Remember, the way that we're going to handle this, or any negative exponent algebraically, if it's in the top, we push it to the bottom and make the exponent positive, and vice versa. If it's in the bottom, we push it to the top and make it positive. So here, I'm going to take that x squared plus 1 to the negative 1/2 power, push it to the bottom of my fraction. I'm pushing it down in my denominator with my 2, and that's going to make the exponent positive. So we multiply by 2x, which is easy enough to do, because 1 times 2x is going to make my numerator 2x, divided by 2 times x squared plus 1 to the positive 1/2 power. Anything over itself is going to cancel. So in this case, my 2's will cancel. So my answer ends up being x divided by the square root of x squared plus 1. Now, the reason I reintroduced that square root, technically, you could have written this as x squared plus 1 to the 1/2 power. But remember, anything to the 1/2 power is the square root of that same anything. All right, so I'll accept either or. If you gave me x divided by x squared plus 1 to the positive 1/2, you got rid of your negative exponent, so that's the correct answer. But if you also wrote it with the square root, it's the same thing algebraically. All right. Any questions on example 1? All right, example 2. Here we're asked to differentiate two different trigonometric functions and apply the chain rule. For part A, we're given the function y is equal to sine of x squared. And for part B, we're given y is equal to sine squared of x. All right, so for part A, well, y is equal to sine of x squared. In the last section, the derivative of trigonometric functions, if we had been asked to find the derivative of sine of x, that's a simple problem. We could just simply look at the chart and just pull the derivative of sine of x. So what makes this difference is that if we're not differentiating the sine of x, or a regular trigonometric function, we're differentiating the sine of x squared, which means we have to introduce parentheses because what we're taking the sine of is a little different than just some variable. Now, this is going to help us define my inner and my outer functions. Let's check for understanding. Brave, so what's my inner function here? X squared. What about my outer function? Sine of x. All right. Now, just to be clear, once we introduce parentheses, what's inside my parentheses? Inner function. For my outer function, I simply replace the parentheses and its contents with x. So here, inner function x squared, inside parentheses, outer function, replace parentheses with x, and we're left with sine of x. All right. So now we can start working with that shorthand definition of the chain rule. Remember, first, it's a derivative of the outer function. My outer function, sine x, the derivative of sine x, remember we can pull that from my chart, the derivative of sine, cosine. So working with our derivative, or y prime, derivative of the outer function, derivative of sine x will be cosine x. Note that I'm not putting an x here, I'm leaving parentheses because we're gonna have to fill it with our inner function again. In the shorthand definition, the shorthand definition, the derivative of the outer function at the inner function just simply means what was inside the parentheses, but inside the parentheses again. So here my inner function was x squared. So I'm gonna put x squared inside. We don't need to multiply this or times the derivative of the inner function. My inner function is x squared, the derivative of x squared. Once again, like in the first example, it's 2x. So we applied the chain rule appropriately. Now we're just going to look to simplify if possible. My coefficient, or 2x, typically goes in front of trigonometric functions. So y prime will be 2x cosine of x squared. So we're done with part A. Part B in example 2. We're given the sine of square, or y is equal to sine squared of x. Now, just like in part A, we're gonna have to introduce some parentheses. Remember, if we think back to trigonometry, sine squared of x, that's really sine of x squared. Now, this is the part that really, this is why people really start to get a little frustrated with these trigonometric functions, because the sine of x squared, part A, and the sine of x squared, part B, sounds exactly the same to the ear. But if we look at it, the inner and the outer functions are exactly the opposite. So here, my inner function, or what's inside my parentheses, would be sine x. But my outer function, replacing the parentheses with x and observing what's on the outside of the parentheses, would be x squared. So it's very similar with the fact that we're dealing with x squared and sine x, but they're the exact opposites, which is going to affect my answer greatly. Here, my inner function x squared, here my inner function sine x, and vice versa. All right, so now that we have our inner and outer functions, we can start working on our derivative, or y prime. That shorthand definition, the derivative of the outer function at the inner function. Here, my outer function, x squared, the derivative of x squared is 2x. Note that I did not put the x down, just left the open parentheses, because this is where we're going to fill in that at the inner function part. So what was inside my parentheses goes inside my parentheses again. So my inner function was sine x, so I'm going to put sine x inside that parentheses again. So we've handled the derivative of the outer function at the inner function. Now we need to multiply by the derivative of the inner function. My inner function, sine x, derivative of sine, cosine. So derivative of sine x, cosine x. And now we're just going to look to simplify if possible. So dy dx, or the derivative of y with respect to x. 2 sine x, cosine x. Now, I only introduced that Lebanese notation to keep you honest. Remember, there's a lot of different ways that we can write a derivative. This is just one of many. So whether we're using the Newton notation, prime, or Lebanese notation, where it looks like we're introducing or it's dy divided by dx, which is red, derivative of y with respect to x, does not make a difference. We need to know those notations. All right. Any questions on example 2, part A or part B? Now, technically, that shorthand definition combined, the power rule and the chain rule together. And we need to have a formal definition combining the two. So it's good to have this in our notes. But remember, this does not add on to that shorthand definition or take away from the formal definition. So once again, we can still lean on that shorthand definition, and it'll encompass the power rule and the chain rule combined. So once again, that shorthand definition is reliable. In the beginning, I suggest that you lean on that. And if the formal definitions never make sense, you can still get them all right. All right, so the power rule combined with the chain rule, it reads, if n is any real number and u is equal to g of x is differentiable, then d dx of u to the nth power would simply be n u to the n minus 1 times du dx. Alternatively, using the Newton notation, d dx of g of x to the nth power is simply n times g of x to the n minus 1 times g prime of x. Now, that first definition that we went over, because we didn't look at the shorthand definition first, it didn't make, typically it doesn't make sense upon first reading it. But if we're wrapping our mind around that shorthand definition, we can see in terms of inner and outer functions that this still holds true. I'll use the Newton notation because typically the Newton notation makes the most sense to people compared to the Leibniz notation. But if we look at that alternative part, remember d dx basically means a derivative with respect to x of some function g of x raised to the n power. Here, my inner function, g of x, the outer function will be x to the n. So the derivative of the outer function, x to the n, at the inner function will be n x to the n minus 1. That's the derivative of the outer function. At the inner function means what was inside goes inside again. So we'll start with g of x as the inner function, still has g of x inside. I'm going to multiply by the derivative of the inner function, or g prime of x. So that shorthand definition still holds true. Now, if that made sense, great. If not, still lean on that shorthand definition because you can still get our problems right. All right, just give me a couple seconds for the ones who still copy. All right, so example 3, more chain rule problems this time. We're asked to differentiate y, which is equal to x cubed minus 1, that entire quantity, raised to the 100th power. All right. Now, to kind of get us reintroduced to that notation, and hopefully this is starting to make a little more sense, the chain rule in this application, I'm going to start using some of that Leibniz notation and showing how we use that shorthand definition to apply the chain rule. So given that this is y, x cubed minus 1 to the 100th power, we can start working on a derivative of y prime, which would be the derivative with respect to x of x cubed minus 1 to the 100th power. All right, so this is just saying that we're going to take the derivative of the problem given with respect to x. Applying the chain rule here, the inner function, x cubed minus 1, outer function, x to the 100th power. Can everybody see that inner and outer function? Or if you have trouble seeing the inner and outer function at this point, could you raise your hand for me? All right, so using that shorthand definition of the chain rule, is the derivative of the outer function at the inner function. So derivative of x to the 100th power would be 100x to the 100 minus 1 power, or the 99th power. That's derivative of the outer function at the inner function means what was inside parentheses goes inside the parentheses again. And we're still multiplying this by the derivative of the inner function. Or in this case, it will be d dx of x cubed minus 1, which is my inner function. Yep. Still simplifying. This is going to give me 100 times x cubed minus 1 to the 99th power. And it's going to be multiplied by 3x squared. And we get that 3x squared by the derivative of x cubed minus 1, derivative of x cubed using the general power rule, 3x squared minus the derivative of 1 is 0, no need for us to write it. Now we want to simplify if possible. We do have factors that we can multiply. Those factors, 100 and 3x squared. So our answer ends up being 300x squared times x cubed minus 1 to the 99th power. And that's actually the simplest way that we can write this answer. All right, any questions on example 3? All right, so just like in the previous sections, you'll see that the calculus parts of the problems aren't that difficult. It's the algebra that can throw you off. Just simply remembering all the algebra rules and how to apply them. All right, so in example 4, the opportunity for us to introduce some algebra to simplify it, as well as using some algebra to introduce our inner and outer functions. All right, so in example 4, we're asked to find f prime of x if f of x is 1 divided by the cube root of x squared plus x plus 1. All right, so remember that any root, that square root, cube root, fourth root, can be rewritten as a fractional exponent. So our algebra rules that we want to remember, or at least they take for granted that everybody does remember, is that the nth root of x to the m power is equal to x to the m over n. This is why the square root of x is x to the 1/2 power, because the square root is understood to have an index of 2. Or where the n is, it will be 2. And if it doesn't, and it does not show a power, it's understood to have a power of 1. So that's the first algebra rule that they take for granted that we know. Remember, the second, a to the negative n power is equal to 1 over a to the positive n power, or how we get rid of those negative exponents. Push it to the bottom, make it positive, or vice versa. If it's already in the bottom, push it to the top and make it positive. Said all that to say that if we apply these algebra rules, we can rewrite f of x as x squared plus x plus 1 raised to the negative 1/3 power. So if we take the fractional exponent, or changing a radical expression to a fractional exponent, this would be 1 over x squared plus x plus 1 to the positive 1/3 power. And to take it from being a quotient, we push it to the top and make the exponent negative. Remember, we don't want negative exponents in our answers, but that's not to say that we can't take advantage of negative exponents to get to our answer. This way, it's not a quotient rule problem. Remember in 2-3, we had quotient rule formula where the numerator was f, the denominator was g. If we just take advantage of this algebra, we don't have to worry about the quotient rule, saying that we already have to worry about the general power rule and the chain rule. All right, so remember, we always want to take the path of least resistance. So here, given that we introduce our parentheses, now we can define our inner and our outer functions and apply the chain rule. Here, my inner function, x squared plus x plus 1. My outer function will be x to the negative 1/3 power. So now we can start working on f prime of x, our derivative. So f prime of x will be the derivative of the outer function at the inner function. Here, my outer function, x to the negative 1/3. We can use our general power rule to take the derivative of x to the negative 1/3, bringing that negative 1/3 out front. X to the negative 1/3 minus 1, or in this case, negative 4/3 power. This is because negative 1/3 minus 1, or negative 1/3 minus 3/3 will give me negative 4/3. This is the derivative of the outer function at the inner function. Simply means what was inside the parentheses goes inside the parentheses again. So we handle the derivative of the outer function at the inner function. It's going to be multiplied by the derivative of the inner function. My inner function here, x squared plus x plus 1. And we still need to take that derivative. So we're just going to put that little slash mark note that we have to apply that derivative formula. Now the derivative of x squared plus x plus 1, the derivative of x squared, 2x. The derivative of x is 1, and the derivative of 1 is 0. No need for us to write it. Everything else comes straight down. And now we want to simplify if possible, taking the factors that can be multiplying, as well as getting rid of that negative exponent. All right. So our final answer here, it ends up being negative 2x plus 1, taking our numerators of -1 and 2x plus 1, excuse me, our factors -1/3 and 2x plus 1. Gives me the numerator -2x plus 1. All right. And this is going to be divided by, remember, this x squared plus x plus 1 to the -4/3 power. The way that we're going to handle that negative exponent, push it to the bottom of our fraction and make it positive. Now remember that 3 was already in the denominator from our factor of -1/3. This is being multiplied by x squared plus x plus 1 to the 4/3 power. And this is f prime of x. Now, this is not the only way that you can present the answer. Remember, fractional exponents can be rewritten with radicals. So we could rewrite this as -2x plus 1, or distribute that -1 in front, which would give me -2x minus 1 over 3 times the cube root of x squared plus x plus 1 raised to the 4th power. All right. Said all that to say there's a couple of ways that you can write this answer. To me personally, this is the simplest way to write, or at least the quickest way for us to get our answer with the least amount of steps. All right. Any questions on example 4? All right, example 5, this time we're asked to find the derivative of the function g of t, which is t minus 2 divided by 2t plus 1, this entire quantity raised to the 9th power. Now, example 5 is when we start mixing and matching some of these rules. Like I said, one rule in and of itself, not that difficult. What becomes difficult outside of the algebra itself is knowing when to use what rule. So for this problem, well, first, let's label our inner and our outer functions. Brave, so what's my inner function? T minus 2 over 2t plus 1. This entire quotient is what's inside my parentheses. So that entire thing is my inner function. So what will my outer function be? X to the 9th, or in this case, t to the 9th, to stay consistent with the variable. All right. So remember, the shorthand definition of the chain rule, derivative of the outer function at the inner function times the derivative of our inner function. All right. So here, working on g prime of t, derivative of the outer function, or the derivative of t to the 9th would be 9t to the 8th. That's the derivative of the outer function. At the inner function means that t minus 2 over 2t plus 1, or what was inside my parentheses, goes inside my parentheses again. All right, so that's the derivative of the outer function at the inner function. Still have to multiply by the derivative, or ddt this time, of the inner function, t minus 2 over 2t plus 1. Now, technically, we've applied the chain rule, but remember, we're going to have to combine the chain, the quotient, and the power rules for this problem. Probably a good idea to take note of that. So we've already applied the chain. In order for us to find ddt of t minus 2 over 2t plus 1, we're going to have to use the quotient rule. And honestly, the general power rule is basically used for every problem. All right, so it's a mix of all three: chain, quotient, and the general power rule. All right, so picking up where we left off here. Now, in order for us to find this part of our problem, ddt of t minus 2 over 2t plus 1, there's going to be a quotient rule that we're going to have to apply, which means we're going to have to find f, or label f and g, as well as find f prime and g prime, respectively. All right, so the next couple lines we're just working on that second part, or ddt of t minus 2 over 2t plus 1. So our numerator is f, or in this case, t minus 2. My denominator is g, or in this case, 2t plus 1. F prime, or the derivative of f, derivative of t, 1 minus the derivative of 2, which is 0. No need for us to write it. And g prime, or the derivative of g, in this case, 2t plus 1, derivative of 2t, 2 plus the derivative of 1, 0. No need for us to write it. All right, so plugging everything into its appropriate place. Technically, we're still working on g prime of t. That 9 times t minus 2 over 2t plus 1 to the 8th power, we haven't touched yet. But we're going to multiply it by ddt of that quotient given to us. So now we're going to start plugging everything in its appropriate place. This is a reminder, quotient rule, f prime g minus f g prime all over g squared. All right. So here we will have 2t plus 1. Should put this in brackets. So we have 2t plus 1 times 1. That's f prime g. Remember, the order in which you multiply makes no difference. So 2 times 1, 1 times 2, same thing. Minus 2 times t minus 2. All of this is being divided by g squared, or in this case, 2t plus 1 raised to the 2nd power. This is kind of cut down on some of this writing. I'm just going to focus on simplifying this part. 2t plus 1 times 1. It's going to give me 2t plus 1. 2 times t minus 2. And remember that we're still subtracting this quantity. That's going to give me 2t minus 4. All of this still been divided by that 2t plus 1 squared. If we distribute this understood -1 here, that changes the sign of that second part of my product. So my numerator is going to be 2t plus 1 minus 2t plus 4. This has all been divided by 2t plus 1 squared. We combine our like terms. 2t and -2t is going to cancel out. 1 plus 4 is going to leave me with a numerator of 5 over 2t plus 1 squared. Now, this is the simplified version of ddt of t minus 2 over 2t plus 1. Now, what we have to do is still input this into the appropriate place of our chain rule and simplify if possible. So still working on g prime of t, without forgetting the first part of my answer, 9 times t minus 2 or 2t plus 1 to the 8th power. And now it's being multiplied by 5 divided by 2t plus 1 squared. Now, if we simplify this, that gives me my final answer of 45 times t minus 2 to the 8th power divided by 2t plus 1 to the 10th. Now that last step takes for granted that you remember a few algebra techniques. Is there any questions on how I got that 45 t minus 2 to the 8 over 2t plus 1 to the 10? All right. So typically, if you have another question, if you have another question after I explain this, just ask. But typically, if people don't understand this step to this step, is that they forget that any fraction raised to an exponent is both the numerator and the denominator raised to that exponent. So this would be t minus 2 to the 8 over 2t plus 1 to the 8, still being multiplied by the fraction 5 over 2t plus 1 squared. Obviously, that 9 times 5, or we can make 9 into a fraction by putting it over 1. 9 times 5 is where 45 comes from. T minus 2 to the 8, still part of my numerator. 2t plus 1 to the 8th times 2t plus 1 to the 2nd. Same base, add the exponents, 8 plus 2, 10. All right. Are there any other questions after that explanation though? Does it go up? That far enough? All right. All right, put a star beside example 5. This is a good candidate to kind of, this is a good way for me to test if you know the quotient rule as well as the chain rule and the general power rule all in one question. So this would be a good test question. All right. All right, example 6. Okay, is anybody still copy for it? All right, example 6. Another type of problem where we're testing more than one differentiation rule at a time. Example 6, we're asked to find a derivative of the equation y, which is equal to 2x plus 1 to the 5th times x cubed minus x plus 1 to the 4th. Just checking for understanding what rules do you think we'll have to apply here? Any idea? Be more specific, which of the 3 we just usually think we're going to use here? And this is for anybody. Power, not quotient though. Product. So it'll be the power rule because we basically use that for every problem. Product rule. And of course the chain rule. Also checking for understanding, how do you know if you have a chain rule problem upon looking at it? Any idea? All right, so in general, this is what I say. If you see, well, one, if they give you a parentheses and it's raised to some power that's above 2 or cube, that's a chain rule problem. Or if it's a fractional exponent, chain rule problem. Just for the simple fact that technically we could write 2x plus 1 times itself 5 times, multiplied and combined like terms, but that's not a very efficient way of doing the problem. So anytime you have parentheses raised to some extraneous power, either really, really big number like 100 in the previous example, or a fractional exponent like 4/3 in the previous example, chain rule. All right. And keep in mind too, sometimes you may have to introduce the parentheses like in those trigonometric problems that we've done so far, as well as use some algebra to introduce parentheses, like the square root of x squared plus x. All right. So we had to know that the square root of something is that same something raised to the 1/2 power. All right. So like I've said before, and like I've said 100 times, you hear me say it 100 times again, these rules in and of themselves, not difficult. Knowing when to use what rule is what really becomes the problem, along with the algebra, of course, because there's a lot of opportunity to make a small mistake. All right, so in example 6, here we're going to have to use product, chain, and of course the power. So we need to first label f and g. So here f on my first differentiable function, 2x plus 1 to the 5th power. G, my second differentiable function, x cubed minus x plus 1 to the 4th. We still need to find f prime and g prime respectively. As a reminder, product rule, F prime G plus FG prime. All right, so in order for us to find F prime, given that F is 2x plus 1 to the fifth, we're going to have to apply the chain rule, or the derivative of the outer function at the inner function times the derivative of the inner function. Here, inner function, 2x plus 1, outer function, x to the fifth. So the derivative of the outer function would be 5x to the fourth. At the inner function means we're going to write what was inside the parentheses again. And then we need to multiply by the derivative of the inner function. Our inner function 2x plus 1, derivative of 2x, 2, the derivative of 1, 0, no need for us to write it. Now, technically, we can simplify this answer by multiplying both 2 and 5, but because we're not, our final answer is an F prime, we're just simply using F prime to get to our final answer. It makes more sense to leave it as a list of factors. And you'll see that the algebra becomes an issue when this problem are typically in the past, that the algebra becomes an issue or factoring. It's easier to pull out your GCF if you have a list of factors already written down. Right. So now we need to find G prime. So given that G is x cubed minus x plus 1 to the fourth, my inner function, x cubed minus x plus 1, my outer function will be x to the fourth. So for G prime, it will be the derivative of the outer function, or the derivative of x to the fourth, which is 4 x cubed. At the inner function simply means what was inside the parentheses goes inside the parentheses again. So we're going to write that x cubed minus x plus 1 inside my parentheses. We're going to multiply by the derivative of the inner function. My inner function, x cubed minus x plus 1, derivative of x cubed, 3x squared, minus the derivative of x, which is 1, plus the derivative of 1, which is 0. No need for us to write. So we have F, G, F prime, and G prime. We can start plugging things into their appropriate place. So with the given information, we can start working on y prime, or the derivative of the given problem. So F prime G, or 5 times 2x plus 1 to the fourth times 2, is being multiplied by x cubed minus x plus 1 to the fourth. So stay consistent with the book, and keep in mind that the order in which you multiply does not matter. As long as we have all the factors listed, it's the same answer. So y prime will start with 5 times x cubed minus x plus 1 to the fourth times 2x plus 1 to the fourth times 2. All right, so F prime is that 5, 2x plus 1 to the fourth and 2, times G, which is x cubed minus x plus 1 to the fourth. All right, so the product rule, that's F prime G plus FG prime. So now we need to multiply 2x plus 1 to the fifth times 4 times x cubed minus x plus 1 cubed times 3x squared minus 1. Stay consistent with the book. They wrote it as, they wrote it out. That's 4 times 2x plus 1 to the fifth times x cubed minus x plus 1 cubed, and it's still being multiplied by that 3x squared minus 1. Now remember, because we're multiplying, and the multiplication is both associative and commutative, the order in which you write these factors makes no difference. So if you wrote it like I see it here, or if you have 5 times 2x plus 1 to the fourth times 2 times x cubed minus x plus 1 to the fourth, exact same thing. All right, so the order in which you multiply makes no difference. And the reason I'm going out of my way to signify this is because at this point, if this was a test question and you got here, you've applied the chain rule appropriately, you applied the product rule appropriately, you applied the power rule appropriately. So if this is a 10-point question, this will get you 9 out of 10 points. All right, the reason I'm saying this is because from here on out, it's basically factoring or it's algebra techniques. Remember, this is a calculus class. I'm not here to test your algebra. But with that being said, in order for you to get a full credit, you must apply the algebra correctly. So to write this simply, what we have to do now is pull out our GCF, or our greatest common factor, between the two factors, which are here and here. It has a lot of components in these factors, but it's technically only two factors. All right. So my GCF between those two values would be 2 times 2x plus 1 to the 4 times x cubed minus x plus 1 cubed. This is what both of these terms have in common. Remember, 4 can be rewritten as 2 times 2. This first term has 4x cubed minus x plus 1s. This term has 3x cubed minus x plus 1s. So the most you can take away from both is 3. Same thing for 2x plus 1. This first term has 4 2x plus 1s. The second term has 5 2x plus 1s. The most you can take away from both is 4. So once we pull out that GCF, what we actually have left over, if we combine our like terms, will be 17x cubed plus 6x squared minus 9x plus 3. In order for us to get that last two final points out of the 10 possible points, you would have to factor out your GCF completely and correctly, as well as combine your like terms if you multiply the terms left over correctly. And for some people, that may not be worth it. Like I said, I'll give you 8, possibly 9 out of 10 points to get to this point, because that's all the calculus, everything out there that is algebra. All right. If you need a further explanation for this one, just hang around. I don't mind going over it. But this is our final answer for example 6. You know what? I think I'll save example 7 and example 8 for the next class. The next class on Wednesday, I plan on having an activity to kind of reinforce the chain rule. I do want you to try some of these homework problems so that you can see where your problems lie, if you have any. Is there anybody still copying from up here? All right, so the homework for this section, if you're in the 8th edition, starts on page 158. I want you to do problems 7, 23, 25, 47, 51, and 55. If you could, I forgot. So if you could assign your name, out. You don't have any questions. If you do, I'll be around to answer any questions that you have. If not, you have a good day, and I'll see you on Wednesday. Remember, try a few of those problems so we can start on that activity and have a good idea of how to start them on Wednesday. All right, guys, have a great day.